In a distant future, after eons of prosperity, the remnants of a once mighty civilization linger in obscurity. Their engineers once commanded entire star systems, reshaping planets and asteroids to erect a vast interstellar domain. Now, in their waning days, all that grandeur has vanished. The universe fades as stars flicker out, signaling its twilight. Across uncountable ages, the heavens have dimmed into perpetual darkness. A universe aged and forsaken. Amidst this bleak expanse, they await oblivion, aware long beforehand of its inevitable approach. Recognizing the universe's inexorable decline, they meticulously sought a final refuge to endure eternity, undertaking their ultimate engineering marvel around a solitary black hole. Using the destroyed worlds as resources, they built a new habitat, encasing themselves in a shell that protected them from the void. In this fragile shell, barely resisting the pull of their celestial guardian, they lived their humble existence. Fading light of the dying stars fell upon their final home, while the black hole was utilized to sustain them. But beyond sustenance, the black hole gave them a profound boon. The black hole gave them time. The identity of the esteemed scientist who unraveled the mysteries of time had faded into obscurity. Yet, the astro-engineers understood that time was not uniform throughout the cosmos. Within the profound gravitational embrace of the black hole, time flowed at a languid pace, while ages transpired beyond its confines. Mere instants elapsed within its vast sphere. Thus, the remnants of the civilization witnessed the unfolding of epochs before their eyes. Aware that they had merely postponed, not thwarted, their inevitable fate, they acknowledged that darkness would inevitably consume them for eternity. Although this narrative is merely speculation, it is based on a scientific concept that has revolutionized our understanding of the universe. More than a century has passed since Einstein's theory of relativity shook the foundations of our understanding of time and space. However, despite seemingly familiarity, time and space harbor many unsolved mysteries. Einstein's theories provide insights into some of them, but they are only superficial. What is the fabric of space? Does time have a tangible existence? The search for answers to these fundamental questions can either illuminate our understanding with sudden clarity or plunge us deeper into the mysterious realms of space and time. The civilization exhausted every effort to stave off their impending demise. Yet despite their endeavors, they could only manipulate reality to a certain extent. They couldn't defy it entirely. Behind it all is surely an idea so simple, so beautiful that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? How could we have been so stupid? John Archibald Wheeler. What is space? Question seems almost meaningless. From childhood, we're taught to navigate our environment, using terms like up, down, left, right, back, and front. We call it three-dimensional, where we are free to explore each dimension. But what is this universal platform on which our lives unfold? This question preoccupied the earliest philosophers around the 4th century BC. Plato suggested that space was the nurse of becoming, the medium of existence, devoid of its own qualities. His student Aristotle agreed with him, rejecting the notion of emptiness. However, more than 2 millennia passed before our modern understanding of space emerged. By the 17th century, modern science had emerged, clarifying the processes of the universe through the formulation of physical laws, moving from mythical narratives to the language of mathematics. In 1632, Galileo, then in his mid-60s, published his groundbreaking work Dialogue concerning the 2 chief world systems. Having faced scrutiny from the Roman Inquisition for his heliocentric views, Galileo opted to avoid controversy. Instead, he spent the intervening years quietly consolidating his numerous ideas on space and the cosmos into a comprehensive book. Within this text, he reflects on the life of a sailor confined below deck in a windowless cabin, surrounded by plates, knives, a goldfish in a bowl, and a collection of birds, flies, and butterflies. What does the sailor experience? When the ship is anchored in port, the cabin is a model of serenity, with everything in its place and the goldfish swimming peacefully in its bowl. However, when the ship encounters rough seas, the cabin becomes chaotic, with plates and cutlery flying off the table and water pouring out of the goldfish bowl. In contrast, when the ship is sailing smoothly, with full sails and calm seas, the cabin returns to a state of calm and serenity, giving the sailor the feeling of being back in port, despite the ship's motion. Galileo observed that within the enclosed cabin of a ship, devoid of windows to perceive external motion, there was no experimental means for a sailor to discern whether the ship was in motion or at rest. From this, he deduced the absence of an absolute frame of reference for rest in space. Instead, he proposed that all individuals perceive smooth, uniform motion similarly, experiencing it as a state of rest. Thus, Galileo asserted the principle of relativity, positing that any uniform motion is relative to any other uniform motion. This concept marked the birth of the first theory of relativity. Galileo's hypothetical sailor, situated on a ship near the Earth's equator, would be subject to multiple motions, rotating at 1,600 kilometers per hour around the Earth, which itself orbits the Sun at 67,000 kilometers per hour, further orbiting the Milky Way at 720,000 kilometers per hour, and ultimately moving toward the Andromeda Galaxy at 403,000 kilometers per hour. Despite the immense journey, spanning millions of kilometers from his initial position, the hypothetical sailor experiences no sensation of motion. Regrettably, upon the publication of his book, Galileo faced condemnation from the Church yet again, being charged with heresy due to his heliocentric interpretation of the cosmos. Consequently, his work was prohibited, remaining on the Church's Index of Forbidden Books until 1835. However, this setback did not mark the conclusion of the story. In the decades following Galileo's ordeal, two prominent European intellectuals engaged in debates concerning the essence of space. Isaac Newton, born in England in 1642, emerged onto the intellectual scene shortly after Galileo's passing. He requires little introduction, being recognized as one of the preeminent thinkers of his era, if not one of the greatest of all time. On the other hand, his counterpart, Gottfried Wilhelm Leibniz, though not forgotten, is relatively less renowned today. Born in 1646, in what is now Germany, Leibniz was a prominent figure of his time, contributing to mathematics and philosophy. Delving into profound metaphysical inquiries, Leibniz grappled with enduring questions that continue to perplex physicists and philosophers. Why is there something rather than nothing? The feud between the two men was sparked during the development of calculus. Although Leibniz published his work first, Newton, serving as the president of the Royal Society at the time, accused him of plagiarism, alleging that Leibniz had stolen his ideas. Newton initiated a committee to investigate the dispute. As expected, the committee sided with Newton, intensifying the ongoing animosity between him and Leibniz. Their discord extended to a second disagreement, centered on a seemingly simple question. What happens to a spinning bucket of water in space? Newton asserted that space was an absolute and universal entity, an unyielding stage upon which all motion unfolded. In a universe devoid of matter to perceive motion, Newton argued that both space and time would persist. Illustrating his point with a thought experiment involving a bucket of water, Newton proposed that if the bucket remained stationary, the water's surface would be flat and level. However, when the bucket was set into rotation, the water would spin along with it, causing the surface to curve. Newton prompted contemplation. What was the water spinning relative to? He posited that the acceleration of the spin was relative to an absolute space, a concept distinct from the rotating object itself. Thus, the rotation of a bucket in a universe devoid of matter would still cause the surface of the water to curve. However, according to Leibniz, attributing properties to empty space in such a universe is nonsense. He argued that the meaning of space depends on the relative position of objects, and similarly, the concept of time has meaning only when discussing the relative motion of objects. According to Leibniz, space and time play no role without matter, and therefore do not exist. Unfortunately, Leibniz died in 1716, and the dispute between him and Newton remained unresolved. In the end, Newton's concepts won out. Absolute space, by its own nature, without reference to anything external, remains always the same and motionless. Absolute, true, and mathematical time by itself, and from its own nature, flows equally, without relation to anything external. Isaac Newton. These ideas of absolute space and time became the dominant scientific framework for nearly 2 centuries. even though Galileo rejected the idea of absolute rest. Although relativity was still part of the discourse, it applied primarily to space. Time was treated as a separate and independent entity by both Newton and Galileo. Time, with its implicit direction, seemed fundamentally different from space. According to Newton, all clocks in the universe tick absolutely synchronously, marking a universal rhythm that governs every event in the cosmos. However, the question arises, is such a view of absolute time really accurate? Is time a malleable construct subject to change, or is it an unwavering metronome that moves the cosmos forward? Does time have intrinsic properties, or is it determined only by the events that unfold in its path? To answer these questions, we need to shift our focus from physicists pondering clocks, rulers, and motion and look into the distant future of a universe where heat reigns supreme around an aging black hole. In this scenario, our dying civilization finds itself in a state of inertia, and their only option becomes to wait in the face of dwindling resources and the fading glow of the stars. Raw energy becomes their most coveted commodity, their means of sustaining existence, as they deliberately slow down all aspects of their lives in a desperate attempt to survive. With heavy eyes, they watch the darkness of the heavens looming, realizing that, as universal heat death looms over the cosmos, time becomes their greatest adversary. You may see a cup of tea fall off a table and break into pieces on the floor, but you will never see the cup gather itself back together and jump back on the table. Stephen Hawking. What, then, is the nature of time? This question has intrigued thinkers throughout history, including those in ancient Greece. Aristotle conceptualized time as merely the interval between before and after, while Hindu philosophers viewed time as cyclical, spanning from creation to destruction over a vast period of 4 billion years. Despite these perspectives, the true essence of time remained elusive. Like space, time appears to be an intrinsic aspect of reality, yet it possesses distinct characteristics. Unlike space, time exhibits directionality with a discernible past and an impending future. Furthermore, unlike space, we cannot traverse time freely. Scientists often adopt a pragmatic approach, focusing on the practicalities of time measurement without delving deeply into its fundamental nature. While a clock serves as a crucial tool for experimenters, it doesn't diminish the importance of addressing the question of time itself. To fully comprehend time, we must initially reflect on horses and steam engines. The onset of the Industrial Revolution posed a significant challenge for humanity. Traditional engines of civilization, such as draft animals like horses and cattle, were relatively straightforward to manage. Understanding how much to feed them and how much work they could perform was a simple matter. However, the emergence of new technologies such as steam engines complicated matters. Determining the productivity of a heap of coal in comparison to a well-fed animal became a pressing economic concern. Would it be financially viable to replace horses with engines if the cost of feeding the engine outweighed its benefits? It was from this conundrum that thermodynamics was born. During the infancy of thermodynamics, it was observed that traditional engines operate at only 3% efficiency. For example, in a physical steam engine, the heat generated by fire is used to boil water, but some of this heat is inevitably lost to the surrounding air. In addition, energy is dissipated through friction when metal parts rub against each other, making loud creaking noises and releasing heat. These forms of energy loss are inherent in any physical steam engine. Within the framework of thermodynamics, it was recognized that perfect efficiency was unattainable. Energy is always lost as heat flows from one place to another. The concentrated energy released by burning coal must decompose as it passes through the engine, resulting in some energy loss to the surrounding space. Eventually, a new concept emerged to explain the inevitable growth of decay and disorder: entropy. And it is probability that determines how it happens. As 20th century physicist George Gamow put it, the room in which you sit reading this book is filled uniformly by air from wall to wall and from floor to ceiling, and it never even occurs to you that the air in the room can unexpectedly collect itself in a far corner, leaving you to suffocate in your chair. However, this horrifying event is not at all physically impossible, but only highly improbable. Gamow points out that the waiting time for such an event is trillions and trillions of times longer than the entire age of the universe. Disorder, or entropy, is statistically much more likely. Thus, using the new laws of thermodynamics, physicists have clarified the inevitable increase in entropy, signaling a movement toward disorder and decay. As the universe progresses, it inexorably moves towards a future characterized by increased disorder and decay compared to the present state. This principle applies not only to individual components like steam engines, but to entire celestial bodies, such as planets, stars, galaxies, and cosmic filaments, all transitioning from order to disorder. In 1862, Lord Kelvin, after whom the temperature unit is named, proposed the grim and logical culmination of these ideas. Although mechanical energy is indestructible, there is a universal tendency to its dissipation, which produces exhaustion of potential energy through the material universe. The result would inevitably be a state of universal rest and death if the universe were finite and left to obey existing laws. Consequently, this vision portrays a universe in a constant state of decline, progressing inevitably towards heat death, with stars extinguishing one by one in a continuous transformation of potential energy into waste, ultimately leaving a dark and depleted universe after trillions of years. One of the greatest minds to study entropy and the arrow of time was the 19th century Scottish scientist James Clerk Maxwell. His discoveries in thermodynamics have had a profound impact on our understanding of heat and gases. Central to his research was the concept of entropy, which led him to consider the consequences of mixing hot and cold gases. Maxwell envisioned a scenario in which, despite the gas's natural tendency toward equilibrium, some demon could selectively manipulate individual atoms, separating the slower ones to one side and the faster ones to the other. In doing so, Maxwell pondered whether this demon could keep the gas warm and prevent it from spontaneously separating into different halves. Realizing that the temperature of a gas correlates with the average velocity of its constituent atoms, the demon's ability to partition the warm gas into unequal halves, one hot and one cold, appears to defy the principles of thermodynamics. By transforming the disordered state of the warm gas into a more ordered arrangement of hot and cold gases, the demon seemingly violates thermodynamic laws. Despite being a mere thought experiment, debates surrounding the implications of Maxwell's demon have persisted for over a century and a half. Some argue that the demon must be expending energy to perform the sorting of gas atoms, thus ensuring that total entropy continues to increase. Conversely, others posit that it is not energy per se that is significant, but rather the utilization of information by the demon, specifically the knowledge of the atom's velocities, to carry out the sorting process. The interplay between energy, entropy, and information in this context may initially appear perplexing. Over the past 3/4 of a century, the relationship between energy, entropy, and information has become increasingly clear. As any encounter with a computer demonstrates, processing information generates a significant amount of heat. However, this relationship is more complex than it appears at first glance. It is not only the process of processing information that generates heat, but also the process of forgetting. Consider a simple arithmetic example. When we add 3 and 2, the answer is obvious: 5. However, if a computer is presented with a sum of 5 and asked what two numbers were added together to get that number, it will not be able to answer as easily. Instead, logic gates within the computer combine electronic signals to perform the addition. But during the calculation process, the original numbers are forgotten as a single answer is obtained. This calculation is irreversible. The original data is effectively lost to the universe. During the forgetting process, the logic gates generate a small amount of heat. In the field of thermodynamics, there is a fundamental threshold of oblivion known as the Landauer limit. This limit defines the inevitable energy release associated with erasing a single bit of information, which was experimentally confirmed in 2012 to be just over 1/100th of an electron volt at room temperature. Scientists suggest that today's computer chips exceed this limit by a factor of thousands, but by 2035, they will likely be approaching it. This tiny amount of heat inexorably contributes to the increase in entropy, not just locally in computer systems, but throughout the universe. The irreversibility inherent in computational processes, in particular the forgetting of information, is a key contributor to the increase in entropy. Consequently, the act of forgetting becomes an integral aspect in determining the arrow of time. Does this mean that the concept of yesterday and tomorrow requires the act of forgetting to give them significance? Does the existence of the future depend on our inability to remember? As it stands, we can imagine our lonely civilization standing on the brink of universal heat death in the distant future, when all usable energy will be exhausted and entropy will reach its peak. Does time retain any meaning in such a situation? We have reached a critical point. Although the established postulates of modern time and space have served us well, they have inherent limitations. Despite their usefulness, a revolution is looming that will inevitably lead us into the twilight of our solitary existence within a black hole. Along this trajectory, we will have to explore new time and new space. Despite the resignation of many civilizations to their inevitable fate, a handful of curious minds persisted, fueled by their remaining energy, in contemplating the mysteries of the universe. Within the pages of ancient tomes that had endured for eons, they encountered narratives of space's ability to bend and warp. At the heart of these narratives lay the tale of light, a phenomenon whose staggering speed had been harnessed to gauge the extent of their dominion. They understood that the speed of light stood as an insurmountable barrier, impervious to their most concerted efforts. Yet they recognized that this cosmic speed limit constituted the initial stride in their prolonged quest to unravel the workings of the universe. When you are next out of doors on a summer night, turn your head towards the zenith. Almost vertically above you will be shining the brightest star of the northern skies, Vega of the Lyre, 26 years away at the speed of light, near enough to the point of no return for us, short-lived creatures. For no man will ever turn homeward beyond Vega to greet again those he knew and loved on Earth. Arthur Clarke. The mystery of the speed of light has forever captivated minds. The first experiments involving the exchange of flashing lights showed that the speed of light far exceeds the speed of sound. This led scientists to wonder, could the speed of light be infinite? Such speculation continued until 1676, when Danish astronomer Ole Roma provided the definitive answer. Roma's careful observations of Jupiter's moons, passing through the shadow of the colossal planet, clarified the true nature of the speed of light. He assumed celestial orbits operated with clockwork precision, enabling him to predict moon eclipses accurately. However, observing Io over time, his predictions initially deteriorated, then improved. It became evident that prediction accuracy relied on our distance from Jupiter, necessitating adjustment for light's extended travel time. With Roma's data, astronomer Christian Huygens calculated light speed to be over 211,000 kilometers per second, close to our modern estimate of about 300,000. This confirmed light's rapid and finite nature. But its true essence remained a mystery for centuries, alongside the perplexing implications of James Clerk Maxwell's ideas. Maxwell famously unified electricity and magnetism, revealing light as a fusion of these forces, governed by equations incorporating its astonishing velocity. Yet, a crucial question lingered. What was this velocity relative to? Maxwell's equations provided no clear answer, prompting physicists to embark on a quest for resolution. Some have suggested that light propagates through an invisible medium, a mysterious ether that permeates the cosmos, implying a universal state of rest, contradicting Galileo's theory of relativity. This idea posed a serious problem. While one group of physicists tried to measure the properties of the ether, others, spurred on by the facts before them, took a different approach. Prominent among them was a young Albert Einstein. He wondered why electricity and magnetism did not obey Galileo's theory of relativity. Why should experiments with these forces reveal absolute motion? In a bold move, he argued that this was not the case. Thus was born the special theory of relativity. Einstein hypothesized that on Galileo's ship, all experiments gave the same results, whether the ship was secured in port or smoothly sailing on a glassy sea. Throwing the ball, it was impossible to determine whether the ship was in motion, but measuring the speed of light would not help either. The constant speed of light in a vacuum seemed to contradict the principles of creation laid out by Newton. In Newtonian mechanics, one could simply add up the velocities, which would result in different measurements for each observer depending on their motion. However, according to Einstein, this did not apply to light. Regardless of the speed of the observer, whether the observer is a stationary ship, moving at 50 knots or 50,000, all will measure the same speed of light. However, if this statement was true, then something else must have changed, and the only variable in the equations remained the fundamental nature of space and time. For the theory to hold, each observer needed their own measurements of space and time. In special relativity, it was the speed of light that remained constant, not space and time. These two dimensions ceased to be the universal backdrop for physical phenomena. Similar to Maxwell's unification of electricity and magnetism, space and time were now on the verge of being joined. Gentlemen, the views of space and time which I wish to lay before you, they are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Hermann Minkowski, 1908. In 1908, Hermann Minkowski, Einstein's former professor, proposed a groundbreaking concept. In response to the revelations of special relativity in 1905, he delved into the geometry underlying these new equations. While Einstein treated space and time as distinct entities, requiring a mixing of the two to transition between observers, Minkowski argued for a simpler approach, merging space and time into a unified entity called space-time, and using geometry to transform one observer's space-time to another. Thus, the concept of combined space-time emerged. This fusion of the three dimensions of space with the dimension of time became known as Minkowski space. Although Minkowski passed away tragically in 1909, before his idea gained full acceptance in the physics community, his proposal signaled a potential upheaval of Newtonian notions of space and time. Yet, Einstein remained dissatisfied. Despite revolutionizing our understanding of the universe, Einstein's theories fell short in explaining gravity. Newton's gravitational equations relied on distances between masses, but special relativity showed discrepancies in defining these distances. Einstein returned to contemplation, spending a decade pondering how gravity might emerge from these challenges. In 1915, he unveiled a solution that rattled the foundations of physics. Building upon Minkowski's geometric interpretation of space-time, Einstein introduced the concept of space-time being malleable. Both space and time could bend and stretch. According to his general theory, mass and energy caused this curvature. Einstein concluded that gravity, as a force, was merely an illusion. Its effects were embedded within the curvature of space-time itself. Newton's traditional depiction of space and time met its demise. Not only were space and time relative, but they were also flexible. The implications of Einstein's theory of relativity quickly unfolded. In the special theory, the passage of time varied with motion. While individuals perceived time passing uniformly, different observers' clocks registered disparate intervals. With the advent of the general theory, time underwent further upheaval. One spatial location began to influence the rhythm of their clock, as the presence of mass curved both space and time. Thus, gravity could govern the relative progression of time. In 1916, Carl Schwarzschild tackled the field equations of relativity for a spherical mass, revealing within his equations the concept of a collapsed mass compressed into a point. Schwarzschild's mathematical formulation provided the framework for understanding black holes. His solution revealed that black holes warp both space and time, creating immense gravitational forces where even light cannot escape. As one approaches the center of a black hole, time becomes increasingly distorted, leading to a significant slowing of its passage compared to clocks in the distant universe near the black hole's core. The implications of Einstein's gravitational theories extended far beyond black holes. Over the centuries, following his insights, numerous other peculiar solutions have been uncovered in relativistic literature. These include concepts like wormholes, warp drives, and entire curved universes, all stemming from the flexible nature of space and time. In 1919, the observation of starlight deflection provided empirical evidence for Einstein's theory, propelling him to celebrity status. Scientists focused on conducting experiments to measure the effects of the general theory of relativity in an effort to solidify its concepts. One particularly unusual experiment was conducted by Joseph Haffel and Richard Keating in 1971. Their setup involved a series of high-precision cesium clocks and a series of flights in a jet airplane circling the Earth. Initially, all clocks were installed in the same location and synchronized. Subsequently, some clocks were transferred to airplanes, with some flying east and others west, some moving in line with the Earth's rotation and others moving against it. The experiment involved spending $7,600 on flights, with 2 seats reserved for Mr. Clock on each plane. As the clock traveled through the air, it experienced different gravitational fields than those left on Earth. After the clocks had circled the globe twice, they were all put together. If the universe adhered to Newton's concept of absolute time, they should have remained perfectly synchronized. However, if Einstein's theory is correct, they should have diverged under the influence of relative motions and the curvature of space-time. The experiment was performed, and after the clocks were reunited, they showed a divergence of a few hundred nanoseconds. Einstein's predictions were confirmed, and he was declared the winner. However, there remained one more test of relativity, perhaps the most impressive in its development. Einstein suggested that space-time could not only stretch but also oscillate and resonate, just as Maxwell had demonstrated that electricity and magnetism could ripple. This phenomenon, known as gravitational waves, presented Einstein with a problem. He pondered the validity of his mathematical predictions, wondering if he had made a mistake. Then, in 1974, a young astronomy student named Russell Hulse, along with his supervisor, Joseph Taylor, made a revolutionary discovery. Using the 300-meter Arecibo telescope, he discovered a pulsar, the rapidly rotating heart of a dead star that emits radio waves. Called PSR B1913 plus 16. This pulsar was spinning 17 times per second and was not a solitary pulsar. It was orbiting around another dead star, a neutron star. By observing the regular pulses of the pulsar, the scientists made an accurate map of its celestial dance. Unexpectedly, they noticed that the orbits of these dead stars were decreasing with time, contradicting predictions based on Newtonian gravity. Taylor and Hulse determined that the stars were gradually moving closer together, and their orbital energy was dissipating into the universe. They subsequently realized that Einstein's gravitational wave theory was a plausible explanation of this phenomenon. They explored the intricacies of the general theory of relativity, calculated how orbiting stars create ripples in space-time, and showed how these ripples can carry away just the right amount of energy to decay the orbit. In 1993, Taylor and Hulse were awarded the Nobel Prize for their discovery. 24 years later, the Nobel Prize was awarded for the direct detection of gravitational waves. The experiment was conducted at the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, which has an amazing sensitivity and ability to detect subtle ripples in space-time. LIGO has ushered in an exciting new era of astronomical observations. It has detected black hole mergers and neutron star collisions. Moreover, astronomers now plan to search for the oldest gravitational waves that have occurred since the origin of the universe. In this new era, shaped by Einstein, it becomes evident that the entire universe speaks the language of gravity, characterized by the curvature and distortion of space-time. Yet, there was another revelation hidden within the equations, initially proposed by Alexander Friedmann in 1922 and later confirmed by Edwin Hubble: the universe's expansion. This expansion entails the continuous stretching of space. Put simply, yesterday there was less space, and tomorrow there will be more. Every galaxy is observed to be moving away from us, including those in our local group, at an average rate of 70 kilometers per second per megaparsec. This means that currently, for every 3.26 million light-years distant from us, a galaxy is receding at an additional speed of 70 kilometers per second. Indeed, a galaxy 326 million light-years away is moving at 7,000 kilometers per second. Now consider a galaxy 32.6 billion light-years away. It is moving away from us at a speed faster than the speed of light. This may seem strange, given our previous knowledge, but the speed limits in the universe only apply to objects moving through space. These galaxies are not moving in space. There is simply space between them. An expanding universe introduces additional complexity in understanding curved and warped space-time, especially when the equations assume that space is infinite. In fact, there is actually a decrease in density in the universe, although this decrease is not uniformly distributed throughout space. For example, individual galaxies are not gradually moving away from each other. Their cohesion is maintained by mutual gravitational forces. In an expanding universe, the boundary between expanding and non-expanding space presents a significant question. What occurs at this juncture? Additionally, expanding space complicates matters further by altering the shape of space-time from one moment to the next, thus challenging what was previously considered a fundamental property of the universe, the conservation of energy. The significance of symmetry in physics, elucidated by mathematician Emmy Noether, is crucial here. Symmetry implies that the laws of physics remain unchanged when your circumstances are altered. In other words, physics remains consistent, regardless of changes in location, ensuring the conservation of momentum. However, in an expanding universe where space-time is in flux, maintaining this symmetry becomes problematic. When space expands, the symmetry of physics is broken. Space doesn't just stretch or erode, it accumulates. However, as photons traverse the expanding universe, they undergo stretching, resulting in a loss of energy, and galaxies gradually lose their momentum and eventually falter. This non-preservation of energy presents an ongoing problem for physicists, complicating our understanding of the cosmos. Now it may seem that space has gained physical reality, given its ability to bend, expand, warp, and pulse. Yet, there is one final twist, articulated by Nobel Prize winner Steven Weinberg. How is it possible for space, which is utterly empty, to expand? How can nothing expand? The answer is space does not expand. Cosmologists sometimes talk about expanding space, but they should know better. To the uninitiated, such a statement may indeed appear perplexing. How could a prominent scientist assert such a notion? Yet, the truth lies in the fact that he is entirely correct. According to Einstein's theory of relativity, space-time is essentially a vacuum, devoid of any inherent properties. Although the mathematics may suggest bending and curving, in reality, space possesses nothingness. However, the concept of time introduces a new dimension to this perspective. In this paradigm, how are seconds, minutes, and hours affected by the advent of relativity? For future civilizations, time held multifaceted meanings. They recognized the uniqueness of their own time, distinct from any other. Moreover, they comprehended that clocks ticked at varying rates, depending on one's location and activities. Their engineers leveraged the flexible nature of space-time to shape their civilization. Utilizing vast portals that warped both time and space, they enabled travel across the empire. Meanwhile, near the gravitational pull of black holes, where time moved slowly, they stretched time to observe the eventual conclusion of everything. People like us that believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. However, Einstein's general theory of relativity presented physicists with a new challenge. They realized that every particle in the universe passes through the past, present, and future. Like a line on a map, they could plot the trajectory of a particle through the 4 dimensions of space-time, outlining its unique path from past to future through a series of present moments. Each particle in your body, including electrons and quarks, moves along its own unique world line in space-time. Initially, these world lines are disparate, but as you evolve, many of them converge into a bundle, forming what we perceive as you. However, once you cease to exist, these world lines are once again dispersed, albeit briefly, in the great annals of the universe. In essence, you exist as an aggregate of these world lines, a fleeting entry in the tapestry of eternity. While this notion may be disconcerting, it seems to be consistent with our understanding. So what then is the problem? First of all, it arises because we are trying to deal with the implications of the relativity of time. In a universe where there is no absolute time, there is no universal cosmic clock. Consequently, there is no such thing as a single present moment, a final instant of now. In a universe where there is no absolute definition of the cosmic now, defining the unique concept of the past becomes a challenge. Similarly, determining where the future begins presents a major conundrum. This dilemma leads to problems in the equations of relativity. The past, present, and future All seem to be predetermined. The entire history of all things seems predetermined and already laid down somewhere in the cosmos. This concept, known as the block universe, troubles many physicists and philosophers, because without a clear now, the cosmos cannot unfold from moment to moment. When we trace our individual world lines, it seems that our paths are predetermined, which calls into question concepts such as free will, and it seems that we are lost. While it may seem intuitive that the past and future are distinct, a closer examination reveals intriguing parallels. Consider two electrons approaching each other. Both possess an identical negative charge, causing them to repel as they draw closer due to electromagnetism. This repulsion intensifies, gradually slowing their motion until they come to a halt and then reverse direction. Eventually, the electrons retreat from each other, retracing their initial paths. On the surface, this scenario appears ordinary. However, if we were to film this interaction and play the footage in reverse, physicists observing the mirrored version would detect no anomalies. The left to right and vice versa switches would go unnoticed by the audience. Indeed, switching left and right doesn't alter the underlying physics. However, what if we took a more radical step? What if, due to clumsiness, we accidentally reversed not left and right, but past and future? The film now runs backward, time itself seemingly reversed. As the audience stares at the screen, they witness a peculiar sight. Two electrons hurtling toward each other, their repulsion growing as they draw nearer. Eventually, they come to a standstill and begin moving away from each other, with nothing appearing out of the ordinary. The audience, familiar with the laws of physics, nods in approval at this seemingly simple demonstration. But how can this be? If we were to reverse the slapstick of Laurel and Hardy, viewers would undoubtedly notice and recognize that something is amiss with the arrow of time. Yet, in the context of the reversed electron scenario, everything appears perfectly ordinary, raising profound questions about the nature of time and its asymmetry. The question arises, why do the electromagnetic interaction between electrons, as well as gravity and the strong nuclear forces, remain constant regardless of the direction of time? Although the weak nuclear forces show small deviations, they are minimal. It appears that at their fundamental level, interactions in the universe have no temporal orientation. Time can flow in any direction without affecting these interactions. In the macroscopic world, we observe, time is closely associated with processes such as coffee cooling, wood burning, and supernova explosions. But these are irreversible actions. They cannot be reversed, just as an egg cannot be returned to its original state. Upon reflection, however, this feature becomes apparent. Our macroscopic world is just a manifestation of the collective behavior of countless atoms. Atoms interact through electromagnetism, a fundamental force. These interactions are independent of the direction of time. So how does the arrow of time emerge from these many interactions? How does time manifest itself? In the simple block model view of the universe, the arrow of time extends infinitely into the past and future. Our universe, however, is different from this block model. It does not stretch infinitely into the past. It began about 14 billion years ago. Although the process that started it remains unknown, observations confirm that the universe had both space and time. The origin of space and time in the universe remains a mystery. Since the birth of the cosmos, space and time have remained its fundamental components. However, there are still mysteries associated with the birth of the universe. Remarkably, it had remarkable characteristics. It was both very hot and dense, yet remarkably homogeneous. This homogeneity led to a characteristic feature. The universe had an exceptionally low entropy from the very beginning. It may seem counterintuitive that homogeneity corresponds to low entropy. After all, a gas scattered throughout a room has more entropy than one in one corner. However, in the context of cosmic matter, this smoothness facilitates gravitational collapse, allowing matter to coalesce into stars and galaxies over time. Consequently, as the universe expands, its entropy increases and gravitational potential energy gradually turns into stars, planets, and people. Eventually, the energy turns into waste heat, dissipating throughout the universe. This transition from low entropy to higher entropy leaves a trace in the cosmos, defining its arrow of time. Nobel laureate Sir Roger Penrose has given much thought to the initial entropy of our universe and concluded that the probability of its random occurrence is incredibly small. Clearly, there must have been something special about the birth of our universe, but what that something was, we still don't know. Does this mean that the block universe is devoid of an innate arrow of time? Would it have become impossible to distinguish between past and future without the Big Bang? Imagining how we would perceive such a universe is very difficult. Perhaps our ability to imagine anything at all is due to the extraordinary circumstances of the universe's origin. On June 10, 1944, a British Halifax bomber, as part of a flotilla of 400 bombers, was flying over France in support of the Normandy landings. However, near the town of Laval, the plane was hit by German anti-aircraft fire and, engulfed in flames, crashed into the French countryside. By tragic accident, all 7 crew members on board were killed in the crash. 7 lives were destroyed in a conflict that ultimately cost millions. The pilot was a 33-year-old Dutch volunteer named Willem Jacob van Stockum. Perhaps not widely known today, but it is to him that the discovery of time travel is credited. By the 1940s, time travel had already become a popular theme in science fiction, most notably in Herbert George Wells's novel, The Time Machine, published half a century earlier. Within the framework of Newtonian physics, however, time travel remained firmly rooted in the realm of fantasy and impossibility. Within the revolutionary paradigm of relativity, however, Van Stockum found a scientific basis for time travel. Despite the mathematical complexity of relativity theory, when Einstein himself doubted that his field equations would find an analytical solution, the first such solution was found just a year after they were presented to the world. This breakthrough paved the way for the exploration of concepts such as black holes. By the 1920s, scientists such as Einstein, Friedman, de Sitter, and others were busy seeking to understand the mathematical structure of the entire universe, unraveling the rules governing the expansion of space, which itself can be curved, and even scenarios in which parallel lines can converge or diverge. Some scientists have explored the mathematical possibilities of hypothetical universes, and Hungarian mathematician Cornelius Lanczos came across a particularly intriguing solution. His equations depicted a universe composed of dust that rotated rigidly. Although this model was nothing like our own universe, it aroused curiosity by its singularity. Van Stockum was intrigued by the trajectories of particles in such a spinning universe. As these particles traveled from past to future, their world lines curved around the universe. However, because of the rotation of the universe, time and space were stretched and distorted. Some world lines completely wrapped around the universe, intersecting each other and forming closed loops. Through these loops, the future repeatedly traveled the path of the past. Physicists call these closed world lines closed time-like paths, but in simpler terms, it is nothing more than time travel. The notion that space and time could be so profoundly distorted as to enable time travel was astonishing. While the concept of a rotating universe might not be entirely plausible in reality, it prompted the exploration of alternative paths to the past or shortcuts to the future. Van Stockum's ambition was to travel to Princeton to collaborate directly with Einstein. However, with the clouds of war looming, he turned his gaze back to Europe. When his homeland fell under occupation, his determination shifted towards joining the fight. Sadly, Van Stockum's own journey came to an end in a French field on a dark night in 1944. Although Van Stockum's name may have faded into oblivion, the concepts of time travel and rotating universes were not forgotten. In 1949, the eccentric mathematician Kurt Gödel returned to them. Today, Gödel is known as one of the greatest logicians of all time, and his famous incompleteness theorem continues to baffle scientists. However, his contribution to physics was no less revolutionary. Fleeing the growing unrest in Europe with the outbreak of World War, Gödel managed to make his way to Princeton University. There, he struck up a close friendship with Einstein, who helped him in his application for American citizenship. It was while studying at Princeton that Gödel redirected his extraordinary mathematical intellect to the study of the theory of relativity and the nature of space-time. In 1949, for Einstein's 70th birthday, Gödel presented him with a solution to the field equations of relativity. Similar to Van Stockholm, Gödel had discovered the mathematical framework of a rotating universe and closed time-like curves that formed loops within his cosmos. Upon receiving this gift, Einstein expressed his disturbance at the possibility, while also noting that Gödel's wife had seemingly knitted him a sweater, which wasn't part of the final present. The reasons for Einstein's death in 1955 and Gödel's in 1978 remain unrecorded by history. Throughout his lifetime, Gödel inquired with astronomers about the potential rotation of the universe, always receiving the same response: no, it isn't. Furthermore, the universe described by Gödel's solution was not our own. However, the prospect that Einstein's theory of relativity could potentially permit time travel reignited interest among researchers, prompting them to revisit their equations. Could time and space be curved enough to allow time travel? Physicists continue to find mathematical reductions of space and time, and there are now many solutions to Einstein's equations in which space and time are extremely warped. This suggests that time travel is theoretically possible within Einstein's theory of relativity. For example, if you add rotation to a black hole, space and time will also twist. In addition, diving through the center of a black hole could lead to appearances in different places. Another concept, the wormhole, could potentially bridge space-time between two places and two different times. Thus, time travel is written into the equations of relativity. Whether enough energy can be concentrated in one place for space-time to bend on its own remains an open question. Although we understand how Einsteinian space-time functions, its essence remains elusive. Where to look for answers? The early 20th century saw a transformative era in theoretical physics, and quantum mechanics led the way. Some speculated that the clue might lie in the smallest scales of the universe. In the distant future, civilization was in dire straits. Stars had long since been extinguished. Matter was disintegrating, and life was almost frozen in the looming darkness. Yet, amidst this desolation, a few souls looked to the sky, watching for the last glimmers of light in the universe. Ancient texts warned of the inevitability of such decay, saying that even black holes would eventually fade into nothingness. While the immense gravitational force of the theory of relativity bound them together on the smallest scale, the actions of the quantum realm caused their ultimate disintegration. For centuries, reconciling the two phenomena was not an easy task. The gravitational world felt distant from the quantum world, and so the demise of the black hole seemed inevitable. Their attempts to stop it proved futile, and the last few people were utterly exhausted, having lost even the will to try. A university student attending lectures on general relativity in the morning and others on quantum mechanics in the afternoon might be forgiven for thinking that his professors are fools or have neglected to communicate with each other for at least a century. Carlo Rovelli. In Tallahassee, Florida, there is a grave in Roselawn Cemetery that bears the name of a man who passed away in 1984 at the age of 82. Unlike other people buried in a cemetery, this man has a plaque in Westminster Abbey in London, next to the resting place of Isaac Newton. Modest at first glance, the plaque identifies him as a physicist and details his birth and death. However, it bears an equation, a complex combination of Latin and Greek symbols. This equation was the first unification of Einstein's theory of relativity and quantum mechanics. Niels Bohr. The famous physicist once remarked that Paul Adrien Maurice Dirac was the most unusual visitor to his institute. Born in Bristol at the dawn of the 20th century, Dirac was not initially destined for a scientific career. Having begun his studies at Cambridge University in 1923, Dirac was known to concentrate on his scientific pursuits. He avoided socializing, and his conversations were mostly terse. His colleagues even coined the term Dirac to represent the unit of 1 word per hour in his honor. Despite his slow speech, Dirac's mind raced through the complexities of physics. It was an exhilarating era for physicists, as Einstein's revolutionary concepts of relativity and the enigmatic implications of quantum mechanics unfolded, with the fundamental mysteries of the universe finally unraveling. As Dirac delved into quantum mechanics, he realized it was rooted in the past. The mathematical frameworks of Schrödinger and Heisenberg unfolded within the confines of Newtonian physics, with its absolute time and Galilean notions of space. Dirac recognized that this conventional view of space and time was antiquated. He believed that the equations of quantum mechanics should align with Einstein's modern conceptions of space-time. This puzzle consumed Dirac, driving him to grapple with the mathematics tirelessly. He would spend his Sundays wandering alone, pondering over the equations in his mind. Then, in December 1927, clarity began to emerge from the fog. He formulated a relativistic quantum equation, one that adhered to Einstein's principle of no special rest frame in the universe. Utilizing this equation, Dirac elucidated the perplexing properties of the electron, rendering them intelligible through mathematics. In Dirac's equation, the electron exhibited behaviors akin to a tiny bar magnet, a manifestation intricately tied to relativity. These characteristics had previously eluded satisfactory explanation. However, the equation unveiled an unexpected revelation. The square root of 1 yielded 2 solutions, both +1 and -1, mirroring each other. In the context of electron dynamics, this meant that the Dirac equation yielded 2 solutions, shedding light on its enigmatic properties. One of the solutions, with negative charge, unambiguously corresponds to the electron. But what does the positive solution correspond to? He first hypothesized that it might be a proton, given its positive charge in the atomic nucleus. However, given its nearly 2,000 times greater mass, this hypothesis proved untenable. Eventually, Dirac realized that his equation predicted the existence of an entirely new particle, the anti-electron. This particle, known as the positron, should have the same mass as the electron, but have the opposite positive charge, representing antimatter. The formulation of the Dirac equation gave rise to quantum field theory, the most triumphant physical concept to date. With these mathematical tools, scientists can clarify the behavior of almost all fundamental particles and forces, a cornerstone of the current standard model. Moreover, for every particle within this model, there is an antiparticle, electrons, positrons, quarks, and antiquarks, all derived from Einstein's concept of relative space and time. Quantum field theory does rely on Einstein's special theory of relativity. But what about gravity and the general theory of relativity? What if we tried to incorporate curved space-time into the Dirac equation? Unfortunately, despite significant early successes, this process has made little progress in the last century. Even within quantum field theory, the underlying quantum wave function on which existence depends unfolds in the context of space and time. However, thanks to the special theory of relativity, this space-time arena is considerably more convoluted than Newton's classical conception. Nevertheless, space and time remain a universal scene, and this stage breaks down when considering the curved space-time of the general theory of relativity. It is very important to remember that in the realm of general relativity, space and time are not static backdrops, but dynamic entities actively forming and evolving. In this narrative, they are not just a stage, but integral participants in the physics of the universe. Quantum mechanics had its difficulties, but after years of effort, physicists managed to curb its various infinities. In curved, bending, pulsating space-time, infinity seemed uncontrollable. Since gravity and quantum mechanics could not be unified, some physicists have redirected their search in another direction, beginning a quest to redefine the very essence of space and time in search of a comprehensive theory of everything. These efforts seek to bridge the microscopic quantum world with the macroscopic world of the general theory of relativity, and thereby provide a complete understanding of the universe. However, these theories of everything do not necessarily simplify the situation. For example, in leading contenders such as string theory or M theory, which postulate the existence of 11 or even 26 dimensions, the fundamental nature of time and space remains a matter of deep investigation. Indeed, the search for a comprehensive theory such as M theory presents a complex picture. In M theory, space and time appear as integral components of the fundamental structure of the universe. Complex shapes formed in multidimensional space offer an explanation not only of space and time, but also of all matter, radiation, and forces. However, the composition of these fundamental structures remains elusive because theory does not provide definitive answers. Another contender in this struggle is loop quantum gravity, which at first glance seems even more mysterious. This theory views space and time as quantum phenomena at their smallest scales. Space-time is presented as a fragmentary entity intricately woven into a network. To our macroscopic perception, this subatomic mesh appears as smooth space and time. However, the fundamental structure of these quantum grains remains a mystery, as they seem to exist without further explanation. Indeed, some have proposed a simpler solution, the notion that space and time may not exist at all. Recall the historical dispute between Newton and Leibniz. Newton saw space and time as inherent components of reality, existing independently of matter in the universe, while Leibniz argued that space and time are determined by the relationships between matter. The relativistic concept of space-time agrees well with this view. Einstein's theory states that matter dictates the structure of space-time, and space-time in turn affects the behavior of matter. In the quantum realm, space-time appears to be granular, which hints at the fundamental construction of the universe from these chunks of space-time as it evolves and expands. But what if space and time don't actually exist? What if space and time are emergent phenomena that we only experience as macroscopic entities? It may seem counterintuitive, but our experience of the universe is constrained by our position within it. For instance, we don't perceive the expansive nature of the cosmos on large scales, nor do we feel the individual impacts of atoms colliding with our skin. Instead, we collectively describe these phenomena using concepts like temperature. Similarly, it's conceivable that space and time operate in a similar manner. In 1997, Juan Maldacena uncovered a significant relationship within the mathematics of string theory and gravity, known as the ADS-CFT correspondence. While this discovery could be coincidental and inconsequential, it might also signify something deeper: the potential path toward unifying quantum mechanics and gravity. This correspondence hints at a deeper connection between disparate aspects of theoretical physics, offering a tantalizing glimpse into the quest for a unified theory. If this path indeed proves fruitful, it will reveal an intriguing revelation. Space and time become granular components of fundamental length and time. These Planck-scale pixels establish the smallest possible resolution of the universe. Consequently, at these minuscule scales, space and time look like nothing more than grains of sand on a vast beach. In this paradigm, the notion of space between these grains of sand, or the time intervals separating them, becomes meaningless. What matters instead are the relationships and interactions between these grains of sand. For us, operating at scales much larger than these Planck-scale grains, the notion of space emerges through these relationships. It is through the complex interplay of these fundamental constituents that we perceive and experience the universe. Thus, the essence of space and time is intricately intertwined with the dynamics of these fundamental building blocks, shaping our perception of reality. Underlying all of this could be the absence of space and time as tangible entities, with only fundamental components and their interactions remaining. This notion might provoke discomfort, as it challenges the notion of individual identity within this relational framework. Perhaps it's helpful to consider it in this way. Many of us have accepted that we are essentially composed of atoms. Our consciousness arises from this arrangement, and we navigate through life with the illusion of our selfhood intact. Similarly, we might need to adopt a similar perspective regarding the context in which our existence unfolds. As we near the culmination of our journey, we reflect on the evolution of our understanding of space and time. Initially perceived as natural and ordinary, they have revealed themselves to be far more enigmatic and intricate. Newton's conception of space and time, as simple and absolute, gave way to Einstein's depiction of curved space-time, and the quantum nature of space-time suggests a fragmentation into minuscule components. Yet despite these advancements, do we truly grasp their essence? There is optimism that forthcoming fundamental theories, potentially a theory of everything, will shed light on the universal truths, including the intrinsic nature of space and time. Perhaps, within such a theory, the notion of the block universe will be dispelled. It's conceivable that quantum processes construct reality, moment by moment, or perhaps there exists an undiscovered process shaping our understanding of reality. After all, despite the tireless efforts of scientists, nature can keep its secrets indefinitely. some mysteries may forever elude our understanding, including the true nature of space and time. As we ponder these mysteries, we return to the twilight of space. At sunset, as black holes slowly evaporate and the universe decays, the last observers cling to the fleeting remnants of time. Despite their mastery of space and manipulation of time, they are powerless against the inexorable march of entropy. And then, consumed by darkness, the saga comes to an end. When we ponder the vast expanse of cosmic history, it reminds us that some questions may remain unanswered. And yet, despite the uncertainty, we continue to explore and seek understanding. Thank you for joining us on this journey. Don't forget to like, subscribe, and share your thoughts in the comments below.